Okay, hello. I prepared this talk on like 24 hours notice, so if it's a little messy, please forgive me for that. But yeah, so I'm Evan from the University of Sydney, and this work was done with Andrew Doherty and Robin Harper here in the audience. And today I'm going to tell you about scalable noise characterization of syndrome extraction circuits with averaged circuit eigenvalue sampling. And hopefully by the end, all of those words will mean something to you. So I guess the first question one might like to ask is, what sort of noise do we want to estimate? Well, useful quantum computation probably requires a fault-tolerant quantum computer with quantum error correction. And so the syndrome extraction circuit is what your quantum computer is going to be doing basically all of the time. And so it is this circuit that you really want to characterize the noise of. And here you have some images from a recent-ish Google surface code scaling experiment. But yeah, so we want to characterize the syndrome extraction circuit, and specifically, we're just going to learn the incoherent Pauli noise associated with each gate, so a circuit-level noise model. And in particular, what we're interested in is learning the noise on each gate when it's operated in the context of a particular gate layer. So when you're doing this syndrome extraction circuit in an experiment, like in this Google experiment, you'll do a set of gates at one time. So for example, you might want to learn the single qubit Pauli noise channel associated with this Hadamard here in the context of that layer, that first layer A. Or, for example, this X gate here in the top left, it occurs again in layer E. But because the contexts are different, you can just like learn these. You want to learn these completely separately. And this will basically tell you like the average noise correlations between the gates in the layer. And so you just do this by estimating the Pauli error probabilities of the Pauli noise channel associated with each gate. That's the overall goal. But I'll go into more details later. And so why do we care about incoherent Pauli noise? Well, you can just do Pauli-Fram randomization or randomized compiling, and it will turn your coherent noise into incoherent noise, and then you just never have to think about it again. At least, I never have to think about it again. And in fact, quantum error correction kind of does the same thing because you're constantly doing these like projective multi-qubit Pauli measurements. So that's kind of nice, and we can just forget about coherent noise. How do we measure this noise? Well, at a high level, what we're going to do is we're going to estimate the noise associated with circuits constructed by rearranging the original circuit layers. So parameterize these by these things that I'm going to call tuples, or like permutations with repetition. So here's my own figure of this syndrome extraction circuit that I laboriously constructed in Blender. Hopefully it kind of makes sense. But the idea is that you have these circuit layers, 1 to all the way up to 9, that you perform sequentially throughout time. But for your noise characterization experiment, rather than just doing the original circuit, you can do any permutation with repetition of these circuit layers. And so what you want to do is choose good rearrangements of the circuit layers that allow you to sample efficiently estimate the noise on all of the gates in the circuit. And then we can extract the gate noise by using a sufficiently varied set of these rearrangements or tuples to get all that gate noise. And this sort of assumes that the noise is not temporally correlated, but we can choose tuples and that sort of preserve this property, and the syndrome extraction circuit itself is sort of designed to realize this. So maybe I can explain what's going on a bit better. This is a 3-qubit rotated surface code. The Z checks are the lighter blue. The X checks are the darker blue. The yellows qubits, are the data qubits. The blue are the measure qubits. And then we have this layer of Hadamards in red and X gates in gray. And so we see that we have, in layer 5 here, this whole layer of dynamically decoupling X gates that mean that every CZ gate layer, the even-numbered layers, is separated by a single qubit layer that is designed to like reduce temporal correlations in the noise. So hopefully that shouldn't be a big issue, but I'm not going to worry about that further here, except to like choose tuples that respect this property of always having a single qubit gate layer between any two qubit gate layers. And so why are we interested in these circuit layer rearrangements? Well, it's basically because the syndrome extraction circuit for a topological code is sort of morally the same regardless of the code distance, right? Because if you have a distance 3 surface code, well, you're doing this, but on a smaller patch. And if you have a distance 25 surface code, you're doing this same circuit, but just bigger, right? And so the idea is that the performance of a tuple set is sort of empirically precisely predictable as a function of the surface code distance. So you can just like design a sample-efficient noise characterization experiment at a small surface code distance, where you can just like tractably do this on your laptop, and then transfer it up to a really big surface code, say a distance 25 surface code, and get a performant noise characterization experiment where you can actually precisely predict how performant that experiment is going to be. So let me dive into some of the details a little more now. So just a brief introduction to Pauli channels for people who are not familiar. So a Pauli channel acts on a state by applying some Pauli operators according to some probability distribution. And so you just characterize this Pauli noise channel by estimating the probabilities of each of these Pauli errors. Now, in general, the probability distribution could be subnormalized if there's like leakage or something, but we're not going to worry about that because, spoiler alert, we're just doing stabilizer circuit simulations here. So we're just going to assume that we have a normalized probability distribution and just estimate that. And the way that we're going to do this is by looking at the eigenvalues of the Pauli channel, which are basically some sort of discrete Fourier transform of the Pauli error probabilities. So you have a Pauli channel. The eigen operators or the eigenvectors are the Pauli operators themselves, and you get these eigenvalues that are basically these sums of the Pauli error probabilities with some sign factor that tells you like whether the Pauli commutes or anti-commutes with the relevant error. And so the broad idea behind average circuit eigenvalue sampling is that we construct some design matrix by doing some stabilizer simulations to track states as they go through the circuit, to determine how the gate eigenvalues, which tell you the noise associated with each individual gate in the circuit, comprises some circuit eigenvalue that tells you the noise across the whole circuit that you're implementing. And so the entries of this design matrix tell you the powers of the gate eigenvalues, right? And you can just calculate this directly. I have an example on the next slide, so hopefully this will make a bit more sense then. And then you can just estimate these circuit level eigenvalues by preparing Pauli eigenstates, doing the circuit, and then doing a Pauli basis measurement, and then you just like use the sample average as the estimator for the circuit eigenvalue. So here's an example of some 3-qubit circuit, like just a toy circuit, rearranged by some tuple. So you have first the second layer, right? Because you have two, like the tuple reads 2, 1, 3, 2, and so you use layer 2 of this circuit, layer 1, layer 3, and then layer 2. And you see that I've got this like 2-qubit Pauli here on this first CZ in the second gate layer. Sort of forgive the kind of awkward indexing, but the idea is that you just look at this XZ Pauli, which is going through this CZ gate, and that corresponds to this eigenvalue, the gate eigenvalue here. And then after it propagates through that, in the first gate layer, after that, you have Xi on this CZ, corresponding to this gate eigenvalue here. And then after that, you get X on the phase gate here, and Z on the Hadamard, followed by, finally, you have IY on this CZ, and you have an X on this Hadamard corresponding to these two gate eigenvalues. And so the idea is that you prepare an eigenstate of Xz, you feed it through the circuit, you measure in the X, Y, X basis, and then you take the sample average, and you use that to estimate this circuit eigenvalue. And this tells you about something about this product gate eigenvalues. And so the other interesting thing to note here is that you can have you need in general a lot of these circuit eigenvalues and a lot of these tuples to get enough information about all of these gate eigenvalues to reconstruct all of the noise in the circuit. So what in general you're going to do is you're going to use a set of these tuples or a tuple set. The simplest one that you could imagine is that you just do layer 1 and then measure. Like your tuples are just layer 1, layer 2 by itself, and then layer 3 by itself, and then no tuple, no gates. So the no gate tuple will tell you about the measurement noise, and then the rest will tell you about the gate noise. And that's sort of the basic tuple set, or the most simple one that you could use. And so once you have a tuple set, you have a bunch of, you need some sort of rule for picking which circuit eigenvalues you generate from the tuple set. And so basically, we choose a rule where you have all of the Paulis that are supported by the gates appearing in the circuit. So here you'll have all of the single qubit Paulis. You want the circuit eigenvalues for those. And then you want the 2 qubit Paulis between qubits 1 and 2 and 2 and 3. But because there's no gate between qubits 1 and 3, you won't have any 2 qubit Pauli preparations there. And I guess for interest, the other thing to note is that when you learn these gate eigenvalues, what you're actually learning, once you turn them back into Pauli error probabilities, is the marginal of the full n-qubit Pauli channel associated with the layer onto the qubits in the gate. So for example, in the first layer 2, when you learn the noise on this C's edge, you learn the marginal of the full 3 qubit Pauli channel onto those 2 qubits, the marginal Pauli error probabilities. But anyway, so once you have this big set of circuit eigenvalues, you can just take the logarithm of the equation that I showed you previously, and then you just have linear regression, right? It's a linear regression problem, and as long as this design matrix is full rank, so as long as you've got sufficiently many circuit eigenvalues, you can just do linear least squares to estimate your gate eigenvalues from the circuit eigenvalues. I mean, you have to take a logarithm, but that's all fine. And this is all basically previous work, or, well, not exactly, because this framing on these circuit layer rearrangements that allow us to design natural noise characterization experiments for syndrome extraction circuits is novel, but the rest of it was just in the original paper on ACES, but we provide explicit implementation details, and we improve upon the least squares estimation procedure, and we're going to precisely describe the performance of ACES noise characterization experiments. I'm not going to go into too many details here because, well, I didn't originally when I made these slides for a different presentation, and probably you would just forget them anyway. The other things that we did was provide routines for optimizing ACES experimental designs according to their figure of merit. So we can basically use our performance predictions to tell us how well is a particular noise, how sample efficient a particular noise characterization experiment is, and design better ones. We demonstrate these methods at scale. So we've simulated noise characterization of the syndrome extraction circuit of a distance 25 surface codes with over 1,000 qubits, and I did it all on my laptop, which is pretty cool. So if there are any questions before I go into a bit more detail on all of these, I'd be happy to take them now, or if not, I will, Luke.
It's a bit surprising you're able to simulate over 1,000 qubits on your laptop.
Well, these are stabilizer circuit simulations, so Craig Gidney's STIM was a big help here. So first, how do you improve the least squares estimation? So in the original paper, Steve Flamia just did ordinary least squares. But basically, you can calculate the covariance matrix associated with all of your circuit eigenvalue estimators just from the circuits that you plan to run on your quantum device. Because basically, you want to estimate multiple circuit eigenvalues at once. And so this will predictably correlate your estimators. And then you can just use this to perform generalized or weighted least squares by like incorporating this estimated circuit eigenvalue estimator covariance matrix. And this will improve your estimation accuracy quite a bit in general. This figure of merit that I was talking about a bit earlier, you can just, it's basically the expected normalized root mean squared error of your gate eigenvalue estimator vector. So you're estimating some vector of gate eigenvalues, and you just want this 2 norm to be small. And one of the things that this accounts for is the time taken to implement experiments. So people often talk about relative precision estimation of noise, where your estimation accuracy scales with how big the noise is. So like if noise is improbable, then you want to estimate it more accurately. And the slight problem with this is that when you repeat a gate a lot of times, which is sort of the trick that people use to get relative precision estimation going, that means that your circuit takes longer on your device. And so in a fixed window of time, you can collect fewer samples from the device. And so we account for this with our figure of merit. And then you're doing a bunch of experiments. You want to like optimize, OK, some experiments might need more samples, and some might need fewer samples. So you can just do gradient descent on this figure of merit with respect to some like weights to optimize that. So yeah, a brief aside on this relative precision estimation. So up the top, when you don't optimize your experimental designs, this is just a toy model. Don't worry too much about the details. But when you don't optimize your experimental designs, the performance is just flat with the gate eigenvalues that you're estimating. When you do optimize your designs but don't account for the amount of time taken, you get the usual relative precision estimation of noise. The slope of this is approximately 1. But when you account for the amount of time taken to perform the gates, then you get this, this line has basically a gradient of 1/2. So you get this square root 1 minus lambda scaling instead of the full 1 minus lambda. I don't think this is a problem with ACES, though, to be clear. I think this is just like a general observation about relative precision estimation of noise. It's not really possible if you account for the amount of time taken to do the gates. Another thing to say, I guess, is that when we're doing all of these optimizations, we just sort of have to assume what the average level of noise is in the device, because this figure of merit and this optimization is all done with respect to the noise, and we don't actually know the noise in a device before we characterize it. So we can just do this with respect to depolarizing noise, and then all we need is like a sort of picture of the average noise level in the device. We assume that it's depolarizing, do this evaluation, and then for simulations, we check it against this random noise model that I just came up to basically test the protocol, where I just choose the Pauli error probabilities independently and log normally distributed associated with each gate. So each gate has its own Pauli error probabilities that we pick separately, and you just use some experimentally relevant parameters following this recent Google experiment. So on to the results. First, we can look and check, one, does this optimization procedure actually improve the estimation accuracy? And the answer is yes, because these things in blue over here for the optimized experimental design are to the left of this thing in red on the right, with a smaller normalized root mean squared error between the gate eigenvalue estimator and the true gate eigenvalues. So this is at like 10 to the 8 shots collected across the experiment, normalized for time. But this error here like normalizes for the, accounts for the amount of shots that you're taking. And the other thing to note is that these curves, which are the predicted performance distributions that we can just calculate from our covariance matrix, line up very precisely with the histograms, which are over 1,000 shots for a fixed but random Pauli noise model. And this is on a distance through surface code. But we see that our performance predictions are really good. The histograms line up really nicely. Another thing that we might like to compare is the predicted performance distributions for ordinary, weighted, and generalized least squares. So I said earlier that you can improve your estimation, and this is the proof. You have these different curves corresponding to increasing accuracy when you use more of the covariance matrix information that you have. The other thing to note, I guess, is that the peak of this red here is about square root 2, approximately, better than this in this generalized least squares one in green. So that corresponds to about a factor of 2 increase in the sample efficiency of the experiment. But we're going to focus today on weighted least squares because weighted least squares is more scalable because when you have a distance 25 surface code, your covariance matrix is like 200,000 by 200,000, and you're not inverting that anytime soon on a laptop, so we just stuck with weighted least squares. And so we can look at the performance of some optimized experimental design that we had earlier as a function of the surface code distance. And so what we see is the performance gets worse a little bit. Smaller figures of merit are better, but sort of tapers off. And in particular, for depolarizing noise, what we can do is fit some traces of some matrices, and we find that these scale almost exactly as a quadratic in this surface code distance. So the relative errors on the data points are something like 10 to the minus 10. So we basically can extremely precisely predict the performance scaling of the noise characterization experiment as a function of the code distance. For log normal noise, it's a little different because here I've taken a bunch of different random log normal noise models and taken the mean of the figure of merit, and then the error bars, they're 2 standard deviations because if there were 1, you couldn't really see them. And so you can look both at the figure of merit, which is the means of those Gaussians, or roughly Gaussians that I showed you just before, and this standard deviation is just the standard deviation of that. And so we find, as we increase the code distance, the standard deviation improves, so your noise characterization experiment's performance becomes more consistent for larger codes because all of the randomness sort of washes out. And then you can also look at, okay, you have this random log normal Pauli noise model. How does the figure of merit change for different random draws of the noise model? Maybe it could be the case that sometimes your noise characterization experiment will perform really well, and sometimes it'll perform really badly because you just happen to be trying to characterize noise that your experiment was bad at characterizing. But it turns out that that's not really a concern because as you scale up your surface code distance, these histograms of the figure of merit across different draws of the random noise model become narrower. So this effect sort of goes away, which is quite nice. And then, so because we optimized our noise characterization experiments for depolarizing noise and then looked at them for log normal noise, we might also ask, what if we optimized our noise characterization experiment for lower noise levels or higher noise levels than we actually have in the device? So for example, in this Google experiment, we had a measurement error rate of about 2%, 2-qubit error rate of about 0.5%, and it's sort of not pictured here, but the single qubit gate error rate was about 0.075%. And so the design optimized at that depolarizing noise level performed best, that's indicated by the blue square in the middle, for the log normal noise model that had the same average error rates as the depolarizing noise model. But even if you optimize your noise characterization experiment for something with double the measurement noise, half the 2-qubit gate noise, and half the single qubit gate noise, that's this red square on the left here, you only need something like 20% more samples to get the same estimation accuracy. So it's not a huge loss. Yes?
What's the difference between A and B and C?
The difference between A and B and C is that in A, the single qubit gate error rates are half of in B, and in C, they're twice in B. And so B is like the error rates that you would see on the device, at least the average error rates that you would see on the Google device. And so the idea is that, yeah, you don't really need that many more samples, even when you optimize for quite different error rates. So the performance is robust in that way. So then we can move on to a distance 25 surface code. So here is the circuit eigenvalue estimation errors. As you increase the measurement budget, you see that you estimate these circuit eigenvalues better and better as you take more samples, which is quite nice. And the plot looks very smooth because you just have so many circuit eigenvalues. Here you're estimating about 200,000 parameters. And then we can look directly at the gate estimation error. So we can look, these plot the histograms of the TVDs between the total variation distance, or the half to one norm, between the true gate error probability distributions and the estimated gate error probability distributions. In the top left, we have the dynamical decoupling and identity gates. So we padded our circuit with identity gates for qubits that are not acted upon by any gate. And so for these gates, we have this plot here. For B, these are the Hadamard gates. C is the measurements. And then D is the CZ 2-qubit gates. And so I guess the main thing to note here, aside from the fact that the different types of gates have different estimation accuracies, the main thing to note is that as you increase the measurement budget by a factor of 10, the gate estimation errors, the median gate estimation errors, decrease by about square root 10. So you get the usual 1 on S sampling that you would expect. And I guess the other thing to say is that the root mean squared, like the normalized root mean squared errors that we predicted from those scaling plots that I showed you earlier match up very closely with what we observed in these simulations. So that's very nice. And so, yeah, this is estimating something like 52,000 gate eigenvalues across all of the gates in the syndrome extraction circuit. So I guess I've gone through this relatively quickly because the last time I gave this talk, I was asked a lot of questions, and so it ended up taking much longer than I expected. But the upshot is that we can simulate noise characterization of a syndrome extraction circuit on over 1,000 qubits with just a laptop, and we can do this performantly. We can predict the performance, and we're able to predict the performance accurately. Paper for this is going to be on the archive soon, and I'm going to be open sourcing all of the code that was used to design and optimize these noise characterization experiments as a Julia package with an overly long name, and coming soon to an IBM device near you. Cool.
Any questions? Anthony.
Thanks for a great talk, Gavin. I was wondering, with the ordering of the layers, you said you put single qubit gates between 2 qubit gates, like reduce temporal errors.
Yes.
Is that also because, it's 2 questions.
Yeah.
I sort of thought, because on superconducting circuits you only have a CZ gate natively, you have to have them there anyway.
Yes.
So how does reducing temporal errors by anything like that compared to, let's say, if you could actually have CZ gates there?
As in, so you don't have to have this layer 5 in general, right? Like you could just do the Hadamards, just not do any dynamical decoupling. But in the Google experiment, they add in this layer 5 here that's just X gates in order to reduce these temporal correlations, if that makes sense. If you do this with CX gates, well, my code doesn't implement dynamical decoupling for that because I looked at this Google experiment and they have CZ gates, so I just used that.
You mentioned that you use the weighted least squares to estimate
Yeah.
a covariance matrix. Have you thought about using like a shrinkage estimator?
Not particularly, no.
It might be good computational. I'm not sure.
I mean, so this estimation, even for the distance 25 thing, because the design matrix is sparse and the covariance matrix is, well, in general, sparse, it's very quick. It takes like a couple seconds. So that is sort of one of the things to keep in mind.
At that point, why not just use like OLS or something?
For ordinary least squares?
Yeah, I mean, didn't you say
That's-
OLS because it's like faster?
So sorry, no, I'm using weighted least squares because it's more accurate, but it's also very fast. And if you're estimating something like 50,000 parameters, you need something fast.
Really?
Thanks for a great talk. For the card, is it, for someone who's not familiar with ACES, is it right to think of correlated, spatial and correlated noise as context dependency inheritance?
Yes. So this is what I was trying to say. So the idea is that when you estimate the noise associated with this CZ gate in this layer 2, you're estimating like the marginal of the full n-qubit channel onto those 2 qubits. So while you don't get like explicit spatial correlations, you're getting the average correlations in the context of the layer.
And then the follow-up is that the n-qubit, one of the marginals in the n-qubit Pauli noise channel that you're working.
Yeah.
Is that model unique, or is that dependent on what sort of experiments you do to extract the different layers?
I mean, up to the assumptions that there aren't any like temporal correlations or something, it should be unique.
And then I have one last short question. So by syndrome extraction of summits, is it meant that you are only looking at some qubit gates and qubit gates, and you're not looking at the same measurement of these noise?
Oh yes. So we aren't specifically accounting like when I'm estimating the measurement noise, which we do, we're not trying to look at any correlations. So like when you actually do the syndrome extraction circuit, you're only going to measure some of the qubits. And so there might be, like the noise might look different when you're only measuring some of the qubits, but we're measuring all of them. So we're not accounting for any correlations, but we are still getting measurement noise characterization, if that makes sense.
Thanks so much.
Any other questions? If not, we have a bit of time until lunch at 12. Now let's thank Evan again.